It's either the project assignment 2 or it's 2 code. Okay, so today we're going to treat a topic which is just variations of the nonlinear equation solution. Okay, but it has a different flavor, and here the quasi-Newton method is even more important. Okay, I'll show you why. But since the first lecture we start treating the nonlinear equation solver and optimizations, there's a basic equivalency. Okay, there's a basic equivalency, but implementation-wise there will be slight difference. Okay, so today we are going through at least you make one practice of that problem. Okay, that you can understand how a nonlinear optimizations the different flavor in the implementation. Okay, although most of the numerical things behind is the same. The quadratic convergence behavior for symbolic derivations, and the is non-quadratic when you do a quasi. Okay, so those are all shared between the two. Okay, I'll show you in a minute. And then following this lecture, okay, because all of a sudden you being generalized to the problem of nonlinear optimizations, which is much more mapped into the real world. Okay, the real world have much more problems that's in the form of nonlinear optimization than the solution of a nonlinear equation. Okay, it just map better. Okay, it's in essence there mathematically there's some equivalency and things, but it just map better. Okay, so I'll introduce two special forms of optimization, okay, in the following two lectures, which each one deserves its own lectures. One is parameter optimization. Okay, you have a parameter space, you write down your objective functions, you ask the questions that within the given system with noise, what is the best parameter that can fit to describe my system in certain way. Okay, so parameter optimization is the first optimizations that's special case. It takes a class to introduce it. Second is geometrical optimization. Okay, something you ask, you know there's a shape, okay, but you don't know what that shape is. Okay, there are two ways of looking at it. The first way is I don't know what that shape is, but I know that shape is smooth. Okay, I know if I make a boat, right, the boat need to be in some shape. I don't know that shape. Okay, but I know if I make anything that's discontinuous, it will cause a lot of turbulence and very difficult to sail. So I know that it should be curved. Okay, then what is the best curve to fit your problem? Okay, so that's come with the idea of spline optimization. Okay, the second class of geometrical optimizations is I know that's a dog. Okay, so and these are the parameter describing the geometry of a dog. So you optimize on those parameters to get out what is most like that dog. Okay, so it's something that is a geometrical optimization. You have prior knowledge of the shape. The other is a prior knowledge of its property. Okay, so geometrical optimization is a special class of optimization that I hope to introduce to you. Okay, so these are 3 lectures in series. Okay, first tell you the general form of the nonlinear optimization. As I mentioned, many times I'll even make slides where I do Newton method to compare how equivalent they are in the nonlinear equation solver. Okay, but it's and how your Sakan method corresponding to your steepest descent and all these things is all there. Okay, so but in general, how the nonlinear optimization work. So now, optimization for nonlinear equations can be generally described by this, right? So you have a Vx, which is your objective functions, and if you have multiple objective function in a optimization, you use Lagrangian multiplier to tie them together. Okay, so you have a scalar single objective function for optimization. Okay, either you want to find the minimum or the maximum, which is nothing but just a minus sign in front of it. Okay, a minimum, if you add a minus sign in front of that v, it becomes a maximum. Okay, so I'll restrict to the problem of minimization. Okay, all the problem can be translated into maximize You want to maximize the objective functions. Just that it flipped the sign. Okay, everything else is almost the same. Okay, so very simply, right? If you look at just the Taylor expansion, the scalar function, if you perturbed it with respect to the vectors of its independent variables, okay, then the Taylor expansion works like this, right? So this is the expansion point, the gradient times the delta x, and this second order term with the Hessian matrix. Okay, so this is for sure. Then there is a something that plus that's on the order of this is the error, right? This is the error that I'm associated with. So this is, sorry, I should change to the approximation sign. Okay, approximation to the second order is something like this. Okay. So if I have a initial guess, just like my Newton-Raphson method, okay, I will search according to these equations, knowing that this is defined as this. Okay, v remains a scalar. This is just the gradient of that scalar. Okay, with respect to all its independent variables. If it has n independent variable, the gradient of that v becomes the factors. Okay. In your physics, this is constantly done if your potential or total energy, right, is your, you try to derive the principle of minimal energy. Okay, then this is saying, take the gradient, then if this is electrostatic energy, this is the electric field. Okay, nothing more, nothing less. Okay, so in here, that this is the vectors, right? The gradient of your objective functions. The Hessian matrix is defined. Where's my Hessian matrix? Sorry, Hessian matrix. Okay, Hessian matrix is like this. Okay, it's something like this. You take the divergence of that gradient function, become the Hessian function. Okay, Hessian functions. Okay, and back to your electrical engineering analogy. Okay, electrostatic potential is something you want to optimize. Take the gradient is electric field. You take the divergence of the electric field. Maxwell equation tell you this is a charge. Why is a matrix? Because it's charge everywhere, right? Charge couple the entire. If you have charge in space, it couple the entire neighboring region. Okay, so this is again can map into directly a physical problem. When I'm asking the minimizations of a potential, the equivalent answer in the physical laws is that what is the charge placement that I get the minimal electrostatic energy. Nothing more, nothing less. Okay, so this is not strange at all. Okay, corresponding one-to-one to the physical systems. Okay, so let's back to in general. Okay, in general for this nonlinear optimization problem. So if the problem is linear, okay, if your v is depend linearly on your n independent variables, okay, I'll leave that to your own practice. You should have done some linear programming, okay, in some classes. Okay, if you haven't done it, don't worry about it. It's very simple. Okay, linear programming, for sure. When you have to solve a very large matrix, the large matrix is still difficult to solve. Okay, don't get me wrong. Okay, but the principle is simple. Okay, in linear programming, if everything is linear, then the optimal point has to be at the boundary. I'm done. Okay, you search the constraint on the boundary, you find the optimal. Okay, this really, if you imagine that if there's a straight line, where is the minimum and maximum? No, that's a silly question, right? Because it must be the two ends. There's really nothing can, if everything is linear, nothing else in the middle can happen. Okay, so the linear programming teaches you that if your v is a linear function to your independent space, your optimal happens at the boundary. Okay, so you have a constraint function for the boundary, you search on the boundary, you get the optimal point. Okay, so this one is not included in our things. Our problem is focusing on if it's nonlinear. Okay, nonlinear, that means a linear function also is characterized by that your Hessian matrix is degenerate. You can imagine if it's only linearly dependent, this will be O0, right? So there's nothing to solve because this is 0, your first order approximation is correct, okay? So this is linear is fine, okay? So now from the equivalency, we say it has a minimal if the Hessian matrix is positive definite, okay? This is derived directly from the Taylor expansion, okay? If this is a good approximation, so if this is positive definite, right? That means if I approximate the V in that region, all the other points except the minimal point, all other points are larger than me. My gradient has to be 0 at the minimal point. Right? Gradient has to be 0. Okay, that's and all the other point is above me, which is governed by the Hessian is positive definite. Okay, you will see a little bit more clearly in just a minute that this one is also teach you how to choose that delta x, okay, in the line search steps, okay. So they will come a little bit very soon, okay. But h to be positive definite, so here this one will be a positive number when this one is less than 0. When when this gradient go to 0, for you search the minimal point, right? This is a positive number. Well, what is that? That means that x plus delta x is always larger than this. Right? Minimal point, right? Minimal point, this term is 0. And this is positive number always, whatever the delta x is. Okay? Positive definite of a matrix, meaning that all factors going through these multiplications will give you a positive number. Okay? And that positive number making this one to be larger than this one. Right? Minimal point. Gradient go to 0. This one is positive. Nothing, no secrecy here. Okay? This is very straightforward. Okay? So then how do we search? Okay? So now you are given this function. You know that your optimal point is when this is go to 0. How do we search that go to 0, right? We need to search just like the nonlinear equation solver. Okay? The difference is your original Jacobian matrix is now the Hessian matrix. So each time, in order to make my gradient to be 0, my search direction is this minus h minus 1 and the gradient v. Okay? If you see this form is why it's like that. This is the Newton search, right? Newton search, your delta x minus your f, which is now is your gradient, right? Is the gradient of v that need to go to 0. So this is your residual function divided by, this should be the Jacobian, right? So Jacobian minus 1. So this is a Newton search for that making fx 0. And here the search is that I make this one go to 0 and that slope is evaluated by the Hessian matrix. And except that, okay, so this is the Newton method for nonlinear optimizations. If I flip between these two, this is the Newton-Raphson method that we introduced. If I flip it between these two, the only difference is here. There's really nothing more, okay? Because the two problems is equivalent, okay? Optimization is a search of the gradient of the objective function go to 0. So equivalent to solving that set of nonlinear equations. Okay, so only this line is different. There's one more, a small difference is here, is the evaluation, okay? When you evaluate the norm, now you evaluate the norm of your step size. And since this is the objective function I'm trying to minimize, you check instead of this residual, which need to go to 0, okay? Most of the optimization problem, you check directly on the objective function. That is the objective. So goal-oriented search, okay? So you print out how good or how small is my objective function. Okay, Newton method, I check how close I am to 0, right? That's the solution of a nonlinear equations, right? In optimization, this is a more common check. You can check your gradient, the norm of your gradient as well, but that's not as direct, right? Checking V directly, is closer to what the problem wants. You're trying to do a minimization of V, right? So you want to know after my nonlinear optimizer, where am I, right? Where is the value of V? How the V go to a minimal value? Okay. So with that, if you do this exactly, meaning that all the evaluations is done symbolically, okay? It's a rigorous Newton implementation, then the quadratic convergence will still be preserved in this guy, okay? This is harder to say because this involves a number. I don't know what is that number, right? Solving this one go to 0 is easier to check, right? Because this one need to go to 0. If this go to 0, I got my solution. Okay, optimization, I really don't know what is the minimal I get to. So it's difficult to define nonlinear convergence, quadratic convergence. Right? Imagine in your program, right? So this is something you have programmed. You can check either the relative norm or the absolute norm. Absolute norm tell you how good is that solution to that nonlinear system directly. Okay? In optimization, because it's a gradient go to 0, but you don't know the absolute number of this absolute minimum of this, right? So the error for this one is harder to define. So you cannot usually check the direct quadratic convergence on V, but you can see the quadratic convergence on the second norm of the relative norm. Okay, that is preserved. Okay, so if your gradient and Hessian is all implemented symbolically that don't contain error, a rigorous Newton method, then when you are close to the minimal, you should observe quadratic convergence on the solution factor norm. Okay, correct solution correction norm. Okay, that should have quadratic convergence. Okay, this clear? Okay. It shares so many things like the Newton method for the nonlinear equation solver. The initial guess is very critical, but very difficult to know. It has the basin of attraction. Whether the initial guess is within that basin of attraction, you will converge. Outside, you will be dead. A line search is necessary, right? Because for overshoot or undershoot problems, right? Whenever you have a local minimum or you have a local maximum, even worse, then you will overshoot like crazy. Okay, so line search. Okay, when you try to apply this delta x, you can put a t here to prevent undershoot or overshoot. So those are the same. Okay, there's really no difference. Okay, all your problem, most of your routines that you write for getting the nonlinear solutions is transferable to here. Okay, transferable to this problem. Okay, I'll give you a practice. Okay, give you a practice to adapt to that. So this is just, I make this gray, remembering that this actually has happened in the 2 lectures before. Okay, 2 lectures before. So now, this is just the definition of minimal, okay, to make sure that you remember minimal is when the gradient go to 0, all the other points is larger than this, so this is when this is positive, okay. Local minimum means R is restricted in a range, okay. Global minimum means it's for all R that's remain true. Okay, so that's just a strict definitions of minimization or optimizations more often has multiple solutions. Okay, so it's just that there are many local minimum. Okay, nonlinear solutions can also have multiple solutions. Okay, so which solution you will go to, or which optimal point you go to, that will depending on your initial guess. Okay, they are in the parametrical space described by delta x. Okay, by x, there can be multiple points that fit the gradient to 0. Hessian is positive definite. Okay, in the nonlinear solution, in that x space, right, there are multiple points that make your fx go to 0. Okay, so that's not strange. Okay. Okay, so let's do one. Okay, so V, this is you can probably see this is adapted, and this one example will be used twice. Okay, so the V is simply I put two equations together, which I have used example. Okay, two equations together, and the norm, second norm of that is my V. This is really a transformations of if this is 0, the minimal point, I already know the answer, right? The minimal point is when this go to 0 and this go to 0. There's really no, it's a one problem. You can observe very clearly where is the optimization point. Okay, but don't laugh at it. Okay, this actually also is a variation when we go for parameter optimizations. It's the same form. Okay, so these things work equally well for parameter optimization. Okay, but for now, just look at it as V is equal to this. Okay, V equal to this. Okay. So now you can do a big paper, write down V, and the gradient V is also you can write down on the paper. This is a closed form. Okay, you take the gradient of that function. It's not hard, but a little bit lengthy. Okay, a little bit lengthy, right? Hessian matrix, you can get it. This taking the second derivative with respect to x1 and x2, you will get a 2x2 matrix symbolically. You can get a big paper and write it down and put that things into your computer. That's fine. Okay, but that's not what I want you to do. Okay, I want you to do that. You have a V, evaluate your gradient and Hessian all in the local analysis. Okay, make it quasi-Newton. Okay, make a perturbation, evaluate the gradient, make the perturbation on the gradient to get your Hessian. Okay, for sure you can do it better with the paper and get a symbolic evaluation. Okay, but that's in optimization that you can see that even for such simple problem, you know, it's pretty messy on paper. Okay, so let's do the quasi thing. Okay, so this is your objective functions. Evaluate using a local analysis to get your gradient. Using gradient as an independent function. Okay, you evaluate a gradient that is a function that do the local analysis, get a gradient. Okay, call that function twice to get your Hessian. Okay, make a perturbation again on the gradient. Okay, to get your Hessian. Okay, and the Hessian is a 2x2 matrix, right? So your gradient. So this question, your gradient is this kind of form, right? And your Hessian is 2x2. Okay, you have two independent variables, and your initial guess will be 0, 0. Okay, let's work it out. And in the first time of your implementation optimization, okay, if you don't know what to implement, please ask me. Okay, so I want to make sure every term is clearly defined for you. Okay, if you don't know how to implement this, okay, for sure this is the first function you should write, right? And you should create a gradient function that return you two numbers, right? And you can write a Hessian things to return you the array. Okay. If you are limited by time, at least finish the gradient implementation of the gradient function. Okay. So that you know how to implement a gradient function. So there should be no doubt in your mind. Anyone close to get done? No. Okay. Due to constraints, okay, please make sure you finish this before Monday's class, okay, because this is going to be used, okay. Before Monday's class, that'll be fine, okay. In the meantime, let me tell you a story that and also tied to how you should debug it, okay. My own PhD thesis, which is for sure 25 years ago, which is a long time ago, I was requiring to write down a transport equations, which it's by itself after spatial discretizations is about half a page large of equations that I need to apply optimization about. Okay, half a page. Okay, for sure. Knowing that symbolically, if I do get the symbolic method for solving the nonlinear optimizations, I'll get much more accurate. Right? I have no problem of all the round-off error or all these things. Okay. So I spend the time. I write down 12 pages of the gradient closed form and the Hessian closed form. Seriously, I still kept those things. Okay. All equations, okay, in that 12 things, okay, and I implement it, okay, and it doesn't converge. What should I do? I don't have this class to attend, so that time I don't know what to do. I was carefully walking through the debugging, and I claimed that my derivation in that 12 pages is all correct, and I complained to my advisor to hell, this is something that's, I've been careful, all the things are possible, just there's no way I can further debug it. If you were me, what you should do? Nonlinear optimization, just the way you are introduced today. What should, if you are given the same problem, okay? That you know all the procedures, but the equation have some complexity. So, but I got this 12 page of equations, and I faithfully implemented in the code. Okay, faithfully. Okay, that time I even tell my advisor I put my life. Okay, there's no error. Okay. But there's an error. Okay, how do you find that? By tracing that 12 page of analytical equations and about, I forgot how many lines are there for the to derive that gradient Hessian. This is what I should do, not as an eventual solution, but to compare is my gradient or Hessian is implemented correctly. Right? Wilkinson principle, right? when one way gets stuck, is the right way to do. Instead of looking at it 100 times to debug, figure out an approximate way to debug. Much better. Okay. I forgot. Is my advisor tell me that, or I finally figure out that I should, instead of checking off that routine, what I should do is implement another method and make comparison. Okay. And indeed, I make that. I found, oh yeah, one of the terms is wrong. Yes. Yeah, so even my carefulness doesn't buy me, okay? But the implement another way, right? I implement term by term, symbolically and numerically. Compare the number, okay? I immediately find, oh, this one of the Hessian elements is wrong. Okay, they're not close. Why they are not close? Okay, and that experience, okay, let me introduce you, even it's all including that experience. There's also something I found, okay. If you look at your Hessian matrix, okay, that your basic calculus should tell you it should be symmetric, right? If that's the same objective function, your second derivative of this, x1 or x2, or x2 or x1, should be identical, right? Again, you will probably be willing to put your life to it and say this has to be identical or there's something wrong. Okay? Numerically, they're not the same. Okay? Very close, but not the same. Okay? Try it. Okay? You see the thing. You will find that if you first perturb your gradient function with x, and then perturb it with x2 to get your Hessian, it's a different number, close. Okay? Then you first perturb it with x2, okay, and evaluate perturb with x1 to get a Hessian. Okay? Number is close, but it's not identical. Okay? So that's not an error. Okay? Just that this is the unfortunate unfortunate consequence of the using a numerical approximation instead of using the symbolic truth. Nothing you can do. Okay, so that's, if you do that quasi in the quasi way, that's just the way it is. Okay, so during your weekend excursion, okay, that's this one. I know there are two solutions, just like the previous nonlinear solvers. There's one minimal point at 1, 1, the other minimal point at minus 1, 1. Okay, look at using 0, 0 and see where your Newton falls. Okay, and do another initial guess. See, this is almost like the game, right? What is that? There's one stupid game now on TV. They use a ball to drop on the peg and then get the money on the wall, something. Yeah, something like that. I forgot that. Yeah, I saw this. Like a Plinko game that they have. So this is almost like the, but it's a bit more optimal. Okay, you can do different initial guess and see where there are two things it should fall to. Okay, and this is a very well-behaved positive definite function. Okay, so so actually you will fall into one of two. Okay, so try that. Okay, try different initial guess falling into different optimal point. Okay, optimal point. And for this problem, like later on your parametric optimization problem. This is one of the very few optimization problem I know what is the value of my objective function when it reach optimal, right? The optimal number is 0, right? That I do know, okay? So this one is even more similar to your nonlinear equation solvers, right? Because I actually know what's my minimal point, okay? Your second norm, this is doing the second norm of the solution of these two equations, right? This is that, okay? So in this problem, it also show you the equivalency between the two. Okay, equivalency between the two. Okay, so have a little bit fun with this. Okay, you are please do implement this before the Monday class. So we do variations. Okay, we can play with that what you have. Okay. So the next questions is that next slides tell you that Newton directions when your H is positive definite, okay, is that positive definite? It is a descent direction, okay? If I'm going for minimal, what does that mean? Okay, your gradient V pointed to the search directions, that it will make your V smaller. Right? It's nothing but this equation, right? So it's when you have expanded in this way, if this is your next solution, right? Next solution minus this is approximately this, right? The error is this term, right? The error is this term. Is the Hessian second derivative is the arrow term, right? So this tells you, and this, if this is always, right, this is positive definite, this is always less than 0, it means, right, taking this delta x is always decrease your objective function. If these remain less than 0, right? So you can see that when gradient or delta x is too large, right, that x is too large, then it may be larger than 0, okay? This one is, if this is not exactly the all factors give you a smaller than 0, some error, okay? And when this is larger than 0, that's the place where you overshoot. Okay? But if your delta x is small enough, okay, then it's guaranteed to be smaller than 0. Okay? Minimum, right? So there's the basin of attraction. Okay? If my delta x is small enough, okay, then this one can be guaranteed to be 0, and that will be, so your Newton method tell you a direction that your objective function will decrease locally. Okay, and if I'm making smaller steps, I'm always making improvement in my search. If you take the full step, there is a chance of overshoot. But within the local, when delta x is very small, the Newton direction always improves the solution. The improvement may be very minimal, but it's a descent direction. Right? Just fine, he tell you, okay? So you can, then you ask the questions of, okay, if I have every time I have to go to gradient and Hessian is so difficult to get, is there a simpler method? Okay? Can I just find a approximate descent function that will continue to give me improvement? I'm willing to sacrifice the quadratic convergence. Okay? I just want to find a direction that is making improvement. And I'm going to correct my variables, independent variables, that way. Okay? Descent, right? If I just find the descent direction, I'm happy. Okay? I'm not working with the Taylor expansion to guarantee if the problem is linear, is solved in one step, or if the problem is linear, I'll have quadratic convergence. I don't have time for forming these large things. I just want to continue to improve my objective function. What is the easiest descent function I can find? The question you ask yourself, okay? Knowing that this is a guaranteed descent direction. But this is difficult to get because you have to go through to get all these inverse of the Hessian times your gradient. Too difficult, okay? You ask yourself, what is the easiest descent directions you can get, okay? And the question comes from the steepest descent method, okay? So this is the descent method, okay? This is my objective function, okay? Objective function. I perturb everyone, okay? Perturb everyone, every independent variables. And I know that I perturbed it increase or decrease the V, right? I can calculate, right? Easily, right? So if it increase, then I decrease delta xi. If it decrease, then I use that delta xi directly. Okay, let me rephrase that, okay? Because steepest descent, okay? I don't want to form the Hessian, okay? So the only thing I can do is my evaluation of V. What I'm doing here, okay, I'm taking the directions of this one minus this by perturbing each individual one, right? When it's a positive number, then I search in the negative direction. Okay? It's a negative number, then I solve in the positive direction, right? So this is for perturbing each independent variable, know the difference, right? And to decide to only search the directions of that change in your xi. Let me rephrase that. Okay, steepest descent means I forget about any of the coupling between the independent variables. I treat every independent variable as independent. Okay, make a local approximations of that slope v with that independent variable, and that is how I'm going to decide to increase or decrease that xi in the next step. I'm done. Okay? And this is called the steepest descent, right? You're standing at the slope. Okay? You have a few directions going down slope, right? So you say, if I go down, if this is down, and this direction is up, so I'm taking the reverse direction, right? So that I'm finding what change in each delta I xi that can independently, they can give me descent functions. If the problem is nonlinear, there's no guarantee that totally it will be a good direction. But this is greedy. I'm greedy, right? I perturb each one and take the direction of whether it's increasing or decreasing, and just take that greedy. I don't care about the coupling. I don't care about the complexity. For each independent variables, I take the greedy direction. Forget about the coupling. Right? So this is called a steepest descent. Okay, so and if you see, this is much easier to implement. Right? There's no Hessian matrix. Right? So each formation of this delta x, the correction step, taking an evaluation of the perturbed value. And I'm done. Right? Here you can see that just if you use the same principle, you just finish your gradient. You haven't even started your Hessian. Right? So this is they call the steepest descent. Okay? A modification of this is that you use the Gauss-Seidel kind of things, right? Whatever has been decided already, you use that for the further perturbation. Whatever is already known that the directions of the x1 is known, you include that in your future evaluations of the objective functions to find the directions whether this one can give you improvement or the reverse direction is something you should take. Okay, so if you observe the difference of this, okay, this one you calculate, right? You perturb each one independently. This one you perturb one, you know delta x1. Right? You perturb 2, you know delta x2. And that is, when you know this, you use that information in your delta x3. Okay, this is Gauss-Seidel. Okay, Gauss-Seidel idea, right? So when I solve instead of Jacobi iteration, right? If I use all my known corrections already, right? Then I can do a better, slightly better on the cause of I will not be able to parallelize this, right? This one you can parallelize this so easily, right? Because all of these are independent evaluations. This one for sure, x1, you first get delta x1, and delta x2 can only be done after you know delta x1. Okay, so this is slower. Not slower, this is something that's sequential. Okay. See, this makes sense? Okay, you probably implement it, and it will make sense. Okay. Okay. Maybe. Okay. So you can ask the next smart question. Okay. These are the lazy people, right? For sure, it's in the old days when computers are a person. you want to find the laziest method to get the solution, right? Because any evaluation is a person doing math on paper, okay? And all this method is all one way or the other tied to some war game, okay, in the beginning phase of this development. Okay, and at that time, whether there is for every canon or things, there are a few computer and tables for corrections. Okay, so whoever can get the canon most accurately to the other side is the side that usually wins. These are life and death for the time. Okay, for the time of this when all these methods being developed. Okay, without a computer. Okay, all these methods is developed in the beginning of the 19th century. Okay, so this method. Okay. Can we be even smarter than this? Okay. Yes, we can. Okay. So this is the famous conjugate gradient. Okay. So now it is better to use all the previous information I have. Okay. So what is conjugate gradient? Okay. If you have delta x from all your steepest descent or the Gauss-Seidel type of things. Okay. When I make a new search, I make sure my search directions is a direction I haven't searched before. Okay, I add in this constraint. Okay, add in constraint. So whenever I use the whatever steepest descent Gauss-Seidel to get my delta x1, I know my previous step what is the correction, right? And I can use this. Very simple linear algebra to make the new correction factor conjugate or orthogonal to the previous search direction. I mean, I don't waste effort in searching in directions I have searched already. Let me say it again, okay? If you have, right, your first step is this, right? You correct it, and you make another advancement of your solution factor. And then you use that to find your second one, right? Second correction factor. You make the conjugate gradient search direction to be orthogonal to the first one by adding part of your first one. To make sure that this one, delta x1 CG, and delta x0, they are orthogonal. Right? Get rid of the search directions that you already searched. Okay, this is conjugate gradient. Okay, and if you apply this, okay, each time, right? Each time you get a new delta x1, okay, you just need to find how does you make it orthogonal to the previous direction. That's actually a very simple operation. Everything is linear. Okay, very simple things to correct. And if your problem is almost linear, okay, this proved to be so effective. Okay, that means that you're going to guarantee convergence in n step, right? You only can have n direction to search if the problem is linear. Okay. There's only that's what is your dimension space. Okay, in n step, if you have a nearly linear problem, the solution will be achieved in less than n steps. Because you have finished all the direction to search. Okay, nonlinearity, a nonlinear problem is not that simple. Conjugate gradient can have poor convergence, just like any other Newton search or things if your initial guess is bad. Okay, but if you're pretty close to your solution, and the problem is pretty linear, okay, then there's a guarantee that n step you have searched all the local space. Okay, so I'll end up here. Remember to finish your the previous example. So I can use that previous example for more variations in the future next two classes. Okay, next two classes.
You'll post the slides.
It's already